So to wrap up Chapter 6, we have Extension 6.7, which is recursively defined sequences. So up until this point, we had our arithmetic sequences, we had our geometric sequences, and we were able to come up with those formulas that helped us jump right to the term number that we wanted. So for example, when we had our geometric sequences, which we just did, remember we had the a sub 1 equal, or a sub n equals a sub 1 times r to the n minus 1 power. This meant that if we wanted to find the 10th term, we could just use this formula. As long as we knew the first term and the common ratio, we could jump right to the 10th term. The way that recursively defined sequences work, it means we're going to be given the first couple terms of a sequence, and we're going to be given an equation that tells us how to get the next term based on the term before. So, for example, if I had this, a sub 1 equals 2, and I knew that a sub n equals a to the n minus 1 plus 3. This right here is my recursive equation, because in order to find the nth term, I have to know this n minus 1 term. This means the term before the nth term. So if I wanted the 4th term, I would need the 3rd term. If I want the 10th term, I would need the 9th term. So for recursively defined sequences, you always have to be given at least the very first term, because otherwise you won't be able to figure anything else out, because the next term depends on the term before it. If we don't know what the term before it is, we can't do anything. So for this one, let's write the first 6 terms of this sequence. So basically what this is saying is, to find a term, take the term before and add 3. So I'm starting with a sub 1 equals 2. That was given to me. So to find my second term, I take term 1, which is 2, and I add 3. So I get 5. To find my third term, I would really be taking my second term, and I'd be adding 3. So my second term is 5, which means my third term is going to be 8. To find my fourth term, I take my third term and add 3. My third term was 8. Add 3 to that and I get 11. So to find my fifth term, you take the fourth. So 11 plus 3 is 14, and I think you can see pretty clearly where this is going. To find the sixth term, you need the fifth. Add 3 to that, so 14 plus 3 gives us 17. Now, let's look at what the graph of that looks like. And again, we only need positive numbers, just like for our other sequences, because we can't have a negative term or anything. Let's see, I'm going up to 17, so 1, 2, 3, 4, 5, 6, and then 2, 4, 6, 8, 10, 12, 14, 16, 17. 17 is right about there. So my first term is 2. My second term is 5, which would be about there. My third term is 8, 2, 4, 6, 8. This should be making, well, you'll see in a minute. Fourth term is 11, which is right about there. So if you look at these, they look pretty linear, which should make sense because this is an arithmetic sequence. I'm just adding 3 each time. So as my term number goes up 1, I'm adding 3. That's a constant rate of change. That's making a straight line. Of course, my graph is a little wonky, so it's not perfectly straight, but you get the right idea. We can do the same thing, though. So this was an arithmetic sequence. We can also look at maybe a geometric sequence. So to do that, let's say our first term is 1, just to make it easy. And our nth term is 3 times the term before. So my first term is 1. My second term is 3 times my first term, or 3 times 1, which gives me 3. My third term is 3 times my second term, or 3 times 3, which is 9. My fourth term is 3 times my third, which is 3 times 9, or 27. Fifth term is 3 times the fourth, which is 3 times 27. That gives me 81. And my sixth term is 3 times my fifth, which is 3 times 81, which is 243. So if you look, just comparing the difference between these two lists of numbers, this one is growing a ton compared to this one, which makes sense. This is really exponential growth when you think about it. So when I graph this, instead of counting by 2's over here, I need to somehow get up to 243. So this is going to be like, let's count by 50's. So 50, 100, 150, 200, 250. And this will be 1, 2, 3, 4, 5, 6. So to graph this, my first term is 1, which you're not even really going to be able to see on this graph. My second term is 3, which is also going to be very low. My third term is 9, which is also very low down there. My fourth term is 27, so that's about halfway to 50. My fifth term is 81, so now I'm getting closer to 100. And my sixth term is 243, so it's going to shoot way up here to almost 250. So if you look at these points, this is obviously not linear, and it has that exponential curve to it. Again, I'm not connecting them because this is a discrete graph, but you can see that that has the exponential growth curve to it. Okay, so finally, when you're given a sequence, you need to be able to come up with the recursive rule for it. So what I would do is, with this first one, my sequence goes -12, -5, 2, 9, 16. It doesn't look like it's growing or decaying especially quickly, so I'm going to think arithmetic first of all. So if I add 7 right here, I'll go from -12 to -5. If I add 7 here, now I'm at 2. Add 7 to get to 9, add 7 to get to 16. So my common difference here is 7. So in order to write a recursive rule, remember you need the first term. So I'd say a sub 1 equals -12. And then to find the nth term, you just need to write what do you do to the term before. So to find the nth term, I take the n minus 1 term and I just add 7. So that was pretty straightforward. Now to look at this one, I can see that this is growing super quickly. That makes me think exponential. I know to go from 3 to 18, that's just multiplying by 6. So what I would do is I would then check, is 18 times 6 108? Is 108 times 6 648? Turns out that it is, so I'm multiplying by 6 each time. So because this is a geometric sequence, this is my common ratio, 6. But again, when I write out a recursive formula, I always have to give the first term, which in this case is 3. And then to get my nth term, I take the term before and I just multiply it by 3. So remember the a sub n minus 1 just means the term before your nth term. So take the previous term and multiply it by 3, and that will give you the next term. The next part of having recursive rules is taking them and turning them into an explicit equation. So an explicit equation is what we learned about before, where you can jump right to the nth term. So if we had a recursive rule that looked like this, a sub 1 equals 9, and then we were given the recursive rule a sub n equals a sub n minus 1 plus 8, what I would do here is I would remember what my recursive rule, what my explicit rule is for an arithmetic sequence. And that's a sub n equals a sub 1 plus n minus 1 times my common difference. And I can use the information given here to put into this, simplify it, and then I'll have an explicit rule as well. So my first term is 9. I'm going to keep the n minus 1 because that is my, my independent variable. That's what I would be putting into the equation. And then my common difference is that 8. That's what I'm adding every time. So then, it doesn't really look like a 9. So then I would take 9 plus, and I need to use the distributive property here, 8n minus 8. And to simplify this, I have 9, I'm taking away 8, so this is 8n plus 1. So my explicit formula would be a sub n equals 8n plus 1. So it's pretty easy to do because I'm really given all the information that I need right here in my recursive rule. I just have to remember that arithmetic rule right there to find the explicit. Now, I can also do this if I have a common ratio. So if I have a sub 1 equals, let's see, 12.5, and a sub n, equals 18, a sub n minus 1. Remember, my recursive rule was given to me here. My explicit rule for a geometric function is a sub n equals a sub 1 times r to the n minus 1 power. So then I'm just going to make my substitutions. A sub n equals 12 times 18 to the n minus 1. And that's all I have to do to come up with the explicit function. I could simplify this a little bit more, but I'm not even going to. I'm going to leave it just like this. So coming up with the explicit rule given the recursive is really straightforward. Okay, we can also go the other direction here. Here's my explicit rule for an arithmetic sequence, and I want to come up with my recursive rule. So remember that for the recursive rule, we need our first term and we need our common difference. So what I would do here, my common difference is that 14, but what I don't know is I don't know my first term. So I'm going to do a sub 1 equals 14 times 1 minus 8. So 14 minus 8 is 6. That should be a 1. So my first term is 6. My common difference is 14. So my recursive formula would be a sub 1 equals 6. And a sub n equals a to the n minus 1, or a sub n minus 1 plus 14. So that was easy enough. And it's really the same way when we have a geometric sequence. If I started with this, a sub n equals 4 times 5 to the n minus 1. Remember, that's my common ratio. So for my recursive formula, I need a first term, and I need to know that this is the term before times r. So all I really need is my first term. So a sub 1 equals 4 times 5 to the 1 minus 1. That would be 4 times 5 to the 0. 5 to the 0 is just 1. So a sub 1 equals 4. So my recursive formula would be a sub 1 equals 4. A sub n equals a sub n minus 1 times 5. And that's all I need to do for those. Okay, and finally, we have a couple special sequences. So, for example, if we have this sequence, 1, 1, 2, 3, 5, 8, and continuing on. This is what we call Fibonacci. This is the Fibonacci sequence, and it's a very special sequence of numbers. It shows up in nature quite a bit. It makes spirals, and there are just all sorts of things you can do with the Fibonacci sequence. You'll hear about it over and over throughout your math career. But if you look, I'm not really multiplying by the same thing every time. I'm not really adding the same thing every time, so it's a little bit harder. And actually what turns out is that if you take the first term plus the second term, you get the third term. 1 plus 1 equals 2. And if you do 1 plus 2, you get 3. And 2 plus 3 equals 5. So in order to find a term, you're taking the two terms before and adding them together. So like a sub 2 plus a sub 3, so second term plus third term equals fourth term. Third term plus fourth term equals fifth term. So what's happening here is we can't really come up with an explicit formula for this. There are a couple of sequences out there that just don't have easy explicit formulas. But what we can do is we can come up with a recursive formula. So a sub n, so if I wanted the third term, I took the term before and the term before that. So the term before is a sub n minus 1. The term before that is a sub n minus 2. And this is how I would write the recursive equation for the Fibonacci sequence. So this one's pretty tricky. You just might have to fool around a little bit with the numbers and see if you can figure out your recursive function.